In this video, we are going to discuss a typical kind of a problem that often comes up related to the vectors. Now, suppose we have an arrangement like this where it's supposedly a triangle, mostly regular shaped bodies. So this is an equilateral triangle. Now, in this equilateral triangle, what we have is that we have three particles in three vertices of that triangle. Let me name them. This is 1, this is 2, and this is 3 in that order. Now, suppose each of the particle tries to move towards the other particle with a constant speed towards the immediately next particle in a given sense. Now, suppose in this sense, what we are saying is that particle 1 moves towards 3 along this direction, suppose particle 3 moves towards 2, and similarly particle 2 will move towards 1 in that order. Suppose it was the other way around, if the case may be, then 1 would have moved towards 2 while 2 would have headed towards 3 and 3 would have headed towards 1. In the process, obviously, because they are changing their positions, so will they change their directions. I'll tell you how. Let me take the example over here, and I suppose consider this displacement over here is, or this initial position, which is the position of 2 with respect to 3, is suppose x in a given time t, and all of them are moving with a constant velocity v, constant velocity or constant speed, so as to say, because the directions are different, so I'll say constant speed v. Now, in a given time del t, suppose this particle would be approaching this first particle, that is from 2 towards 1, and it will be going at a velocity v. So in a time del t, it would have traveled a distance, suppose say v del t, this is v del t, and so would have this particle 3 over here, it would have moved up to here, and that distance again is v del t as well. This is v del t as well. Now, if at this point I was to obtain the position vector, that was x initially, in the time del t has been covered or has passed, so this is in the new position vector from the third particle, which is now present over here, to the second particle, which is now present over here, and this is simply x at t plus del t, isn't it? Because the time has changed from t to t plus del t. Let me write that uh, in a better way. So this is x t plus del t. Now, in these kind of numericals, what we find is that if they are arranged in a regular shaped figure, then as they approach one another, let us say this is approaching, the first one is being approached by 2, and the second one is being approached by 3, because they are changing their positions. Now one would also be approaching 3 in that case. So as 1 approaches 3, 3 is moving along this direction towards 2, 1 is moving towards 3. 1 would have started off over here like this, but with 3 changing its position, one would then be directed along this line. It would have headed off like this, but now it would be aiming at this point. Let us name that point, suppose say A. So one would be aiming at A. Now the path obviously will be changing as it reaches this point. Suppose let us say this is B. As it reaches this point, by the time it is, as it is always looking towards A or towards 3, suppose it will be looking like this towards A at this point of time over here. Similarly, this particle 3 that would be approaching to 2 would have come over here by the time, and 3 while being expected to reach at point A now would be headed towards this point, that is towards, let us name that C. So likewise what happens is that all these points, they tend to converge. They change their path continuously with the change in direction, and they eventually, what they do is like this, they end up meeting at the center exactly. So one with its path continuously changing headed towards the particle 3, it ultimately reaches over here, where 3 also headed towards 2 will reach at that point, and 2 eventually will also reach at that point. Now this is in case of a triangle. It will be the same in case of a square, where the sides are of equal length and they are moving with a constant speed. So here they will be meeting at the centroid of the triangle, and in the square they will be meeting at the center there as well, that is at the intersection of both the diagonals. So in this figure that we first drew, that eventually the displacement will be from one of the vertices towards the center. So the net displacement is in the third figure I will be showing it to you. The net displacement is eventually from a vertex to the center. This is the net displacement. Now we can have a question related to that. It will ask that it's the same way, same question. That is the first question, that is first figure. We can refer to the first figure, and in that what it has asked is that if we have uh, an equilateral triangle of each side supposedly having the length A, then if the particles approach each other at speeds v, every time they are approaching each other at speeds v, then we have to calculate the time taken for them to converge to a point. Obviously they are converging as we noticed over here. So the time that is taken by them to converge, starting off at t is equal to 0 from a vertex. So from their respective vertices, they will be starting off at t is equal to 0, then they will be approaching each other, and in the process they will be headed towards the center and they will be meeting there. So we need to calculate the time. Now in this case we are dealing with the triangle that is at hand, and I have already given you a picture of how we approach it. Now this is one way of approaching. We'll be approaching it both mathematically as well as with physical approach to it, mathematical treatment and the physical treatment to it. We'll be first dealing with the straightforward mathematical treatment, which involves the vectors as well. So here we have x of t plus del t to be it can be said to be the resultant of this vector and this vector that we see over there. There you can see there is a small triangle constructed, and it is the resultant of which two sides? Now one of the sides is obviously xt, but out of that the v del t factor has been reduced. So it is x of t minus v del t. That is the distance from point 3 to 2. That squared, because we are dealing with the magnitude over here. So x t plus del t mod is equal to x t minus v del t squared, plus we'll take the vector addition of those two vectors, v del t squared plus 2 times of xt minus v del t that was there, multiplied with v del t again, and cosine of the angle. Now the cosine of the angle over here, that is the vector, one of the vectors is directed along this direction and the other, this is an equilateral triangle, so the inside of the angle is 60 degrees, but the angle between the two vectors over here is the outer angle, that is 120 degrees. Why? Because the inner angle has the arrows headed towards in the same sense. So the angle between the arrows is this one. One of the arrows is along this direction, the other arrow is along that direction. So the vectors, the angle between the vectors is obviously the exterior angle, that is this one. This is 120 degrees. And so this is cos 120 degrees, and all under root, I can just take the square on the left hand side to avoid the root over term. So what we have is x t plus del t squared is equal to, let me just open this thing for you, x of t squared minus, instead of minus we'll have the plus, I've just opened the bracket, so v square or v del t whole squared, let me write it like that, plus instead minus 2 times of x of t multiplied with v del t plus v del t squared plus, well, cos 120 is simply minus half. 2 and 2 can get cancelled over here, and the minus can be taken to this side over here. So instead of this plus, I have the minus up front. So this is minus of x of t multiplied with v del t. So minus x of t, remember the 2 has got cancelled out, times of v del t. This is the first bit. What about the second one? Minus multiplied with this minus over here, that goes to plus. So plus v del t squared. So finally we end up with x squared t, v del t squared first one, v del t squared second one, and v del t squared third one. So this is plus 3 v del t squared whole square. And the last bit has 2 times of x of t minus 2 times of x of t v del t, and this is again x of t v del t. So minus 3 times of x of t v del t, right? And I just take the x of t to the other side, so x t plus del t squared minus x of t, that can also be taken as square whole squared. And what are we left with? We are left with 3 v square can be taken alone, del t squared, one of the del t stays here, minus x of t is staying, v stays, and del t, one of the del t's can be taken as common. I'll tell you why. Now with all these things done and dusted, what we can do is we can just set another parameter over here. Let x of t be, x of t squared be taken as a of t for our convenience, and x of t plus del t will obviously, that squared will be a t plus of del t alone. And with these things available to us, we will have a change in the above equation. Let's see what's that. We move over to the next page. We'll be referring this page quite often as well. Now here in the considering the previous cases that we have taken, we have, what did we have? We had x of t plus del t to be a, the square of x of t plus del t as a t plus del t, a t plus del t. Then we have minus of a t, and then we have 3 times of v square del t minus x of t v. Now x of t will be something will be simply equal to root over of at minus root over of a of t times of v whole multiplied with del t. Now what we do is we just divide the del t factor onto the left hand side by cross multiplying it. So a t plus del t minus a of t divided by del t, taken limit del t to 0 because we are taking the difference to be infinitesimal, which will be helpful for us in determining the value to our for us to obtain an accurate value. Now this left hand side, as del t goes to 0, is simply, as the left hand side goes to 0, so does the right hand side limit condition applies as well. Del t tends to 0. Now applying the limit on the left hand side, we simply have dA by dt. This is the variation in a with respect to time. What is a? A is simply the root over of x of t. And then we have, now putting the limit on the right hand side, what we get is uh, the first term, that is v squared, that was multiplied with v squared, that goes to 0. And so we have simply minus of 3 root over of a of t multiplied with v. The root over of a can be taken over here. I skip the t because we know it is varying with t. And this is a minus 3v, and the dt has also cross multiplied. So this is dA by root a, and this will be integrated. Now in order to integrate it over a, we need to know the limits what it had with respect to x. Now x of t for t is equal to 0, because we are taking the starting time, is simply x of 0. And what is x of 0? X of 0 was the initial position, which is the distance, and the distance in that point of time was a. So a of 0 will simply be equal to a squared, because a, remember, was x squared. So this is because a, remember, was x of t squared. So x of 0 squared is simply a squared, right? This is starting time. Now they will be meeting at some time. Let that time be t is equal to t0, and that x at t0 is the displacement, or is the position between them. And what is the relative position between them? That reduces to 0. So a at t0 will also be 0, because that is simply x at t0 whole square. So this integration over dA, starting from root over of a, is taken from the lower limit, that is t is equal for t is equal to 0. Remember that lower limit in this case is simply dt. Dt is integrated from t is equal to 0 to t is equal to t0. and t is equal to 0, you have the value of a at 0 as a squared. So this is a squared. That is the lower limit. And what is the upper limit? A of t is equal to 0 at t is equal to t0. So that means we need to just integrate it. This is a to the power minus half. So this is a to the power minus half plus 1 divided by minus half plus 1. That is how we integrate. The formulas are available to you, and this is from a square to 0, lower limit to the upper limit, and this is minus 3v dt is integrated, and that gives t is taken from 0 to any given time t0 when they are meeting uh, at a given point. So this is simply a to the power half, this is half, and this is from a square to 0. This is minus 3 v t0 minus 0, the upper minus the lower limit. Now this is the 2 half that is divided goes to 2, and this is root over of a. Root over of a again is in the form root over of 0 minus root over of a squared, the upper limit and the lower limit taken in the form of the in a value that is a root over. So minus 3 v t0, and so on the left hand side we have minus 2 times of a, that is the distance between that is the length of each side that is given in the triangle, 3 v t0, that is also negative, the negatives can get cancelled out, and what we finally get is that the time taken is simply 2 by 3 a divided by v. Now you can check for the dimension, because a was the distance over there. Distance divided by velocity is definitely going to give me time. So that is exactly the time taken. Now this is one part or one way in which you can solve the numerical that is at hand. So now we can consider the physical treatment to it. We'll be doing the same thing in a more efficient way, because we have just studied the relative cases. So let's get going with that. Now, if you remember the diagram that we had constructed, so this I'm redrawing it. So this is the equilateral triangle, and in that equilateral triangle we have the points as they were 1, 2 and 3, each approaching one another with a constant speed v. Now obviously in a given interval of time del t, I said that this is going headed towards that direction, that is 2 towards 1 and 3 towards 2, and in the process the relative velocity can be considered. Relative velocity of suppose let's just say one of the particles with respect to the other. Now v, let us say this is a v3 with respect to 2, as v32 is simply the modulus of it is going to give me v3, which is obviously v minus v cos 120 degrees, because the angle between them, as I mentioned, is simply 120 degrees. So this is a v3 120 in fact, but this I am writing in case of instead of v2, right? And v2 is v3, which is obviously v. In terms of magnitude, this is simply v, right? Now I can rewrite that. I have a v32 is equal to v minus v cos 120, and that obviously is v minus v cos of 120 is minus half, so this is 3 by 2 v. Now this relative velocity is actually because of the change in position. This relative velocity that we're getting over here, that is actually because of the change in position. How is the position changing? Now let r be the position vector, and that is changing at dr by dt. And as you know, the position vector is getting reduced, the relative position between 3 and 2. Let me take it as r32. What is r32? R32 is simply the relative position that I had taken xt plus del t initially, or x of t. X of t initially is simply r32 in this case, because I'm considering the third and the second particle over here. And that is obviously getting reduced, and because that is getting reduced, I'm considering the magnitude of it, but the magnitude itself is getting reduced to 0. It will be 0, and initially starting, the initial relative position was obviously A. So this minus dr by dt, dr here is the relative position. I'm writing it instead of r32 to 1 1 2 like that. I'm just writing it as dr for simplicity. That is equal to 3 by 2 v. So that gives me minus of dr is equal to 3 by 2 v dt. And as we know, dt is varying from initial time t to a final time, say suppose t0, at which they are meeting, and this position is changing from initially from position that is a to a final position, relative position between them being 0. So then we have dr to be equal to r, but that is in the negative case, and so we can just interchange the limit over here. Because of this negative sign, we can just interchange the limit. A and zeros can get interchanged, right? So we take the positive case over here, dr is integrated to r, and we take the positive, that is from initial limit 0 to the final limit a. 3 by 2 v dt is integrated from 0 to t0, and this is simply a minus 0, the upper limit minus the lower limit, 3 by 2 v, and this is t0 minus 0. Once again the same criteria, so a is equal to 3 by 2 v t0. So that gives me t0 to be equal to the same thing, that is 2a divided by 3v, that which we obtained in the previous case over here. So these two results are obviously the same. As you can see, the approach is obviously different. This is the physical treatment to it. And the other one obviously is the mathematical treatment that we considered over here, taking this vector thing into account, this relative case, this relative condition into account. So there are, you can approach different numericals differently in different manners, but obviously there are convenient ways of doing that. I'm not saying the previous way was not so convenient. It can be convenient in terms of a mathematical treatment, and even at an initial stage you can really prefer that, but this relative case is obviously much easier thing to do rather than anything else. Now in the previous cases, in the previous videos on projectile that I made recently, they also have a relative treatment to them. So the relative treatments are in for problem solving as far as the ease of solving problems is concerned. We'll be doing some more numericals in this related to this case very soon. You can come up with the numericals and mail them to me if you want to. Till then, thank you for watching.